Okay, there you go. So we got. So yeah, the first theorem that we're talking about here is a zero theorem. So what is a zero theorem is asking us is, again, the word zero means your x-intercept or your solution or the factor. So again, we have a lot of name for these zeros, but so make sure you guys know. So what is zero theorem says? Zero theorem says that if you have a polynomial and the polynomial is xn, you know, and so on. So this is your degree. So this polynomial, zero theorem says that if n is your degree, then it has n complex zeros. So what is going on with this zero theorem here, which is very important, is if you have a power 3, you can have 3 complex zero. Now, when they say complex zero, a complex zero means it can be real and or it can be imaginary. So that means that on your graph, so when you do a graph, the graph will show us the real zero. So this is a power 3 graph. The reason why this is a power 3 graph is because this has a 2 turning point. So in this graph, we can tell it only have one real zero. This is called a real zero. This is called a real zero. So your graph can only shows the real zero. But using this zero theorem says that since this is a power of 3, you should have 3 zeros. Since one of these zero is real zero, that means that the other 2 will be imaginary. That means they have to be in A plus BI form. So this is what happens to your zero theorem. So very important here. Again, your graph can only show real zero. The imaginary zero, you have to figure yourself. Your graph will not show the imaginary zero. So if you have something like this, it's telling us that one of these is real, the other 2 is imaginary. Okay, that means it doesn't cross on the x. If your graph is something like this, then all 3 of the zeros are real. That means they are not I form, A plus BI form. Okay. If you have a graph that looks something like this, they're all power 3 here. They all are all power 3 here. Again, this is a power 3 graph. It's not x cubed, it's x cubed plus something. That's why I give you x cubed plus something here. This one also have 3 real zeros, no imaginary. Let's say this is -2 and this is 1. This -2 is a real zero. And this one is also a real zero. But as I mentioned early on in the zero theorem, since you have a power 3, you should have 3 zeros. So if you count this, you only got 2, this one and this one. So where is the third zero will be? You guys want to guess? Karishma, Justin? So this is, so we know this is -2 and this is 1 and this is 3. So these are all your zeros. So we have power 3, so there are 3 zeros here. If you have such case, we know that this is your 0. The other 2 will be imaginary because it never crossed your x-intercept. But for this case, you only got 2 real zeros. So where is the other 0 will be? This is very important. That's why I need to teach you guys all about these zeros. And this is all in 3.4. So where is the other 1 0? We got 1 here, we got 2 here. You should have 3, right? Because of power 3. So anyone know where is the other one? You think this is real or you think this is imaginary? Karishma, Justin, what do you think? You think this is real? Zeros? Because this is real. This is real. So where is the other 0 at? Karishma? What do you think? Just a guess. Real or imaginary? You think this one?
Which one?
This graph I'm talking about.
Oh.
So you got power 3. You should have 3 zeros, right? I got 2 here. Where's the third one?
The third one is imaginary.
That would be wrong. So this is not imaginary. This is real.
Oh wait, it'll be point.
Which
0.5.
it will be him. Because this one has a multiplicity of 2. That means your zeros in this case will be -2, 1, and 1. Why this one has a multiplicity of 2? The reason why is because this touch. So every time when your graph is touching the x-intercept, the x-axis, it is a multiplicity of 2 or 4 or 6 even. So that's the reason why that when you see this, you will have 3 all real zeros, and the zeros are -2, 1, and 1. And I want to point out to you guys here is if you have the same 0, you do not need to duplicate it. So you only have -2 and 1. So this is very important. This is just the first theorem called a zero theorem. Okay. Next thing we're going to talk about here is also very important theorems. This what we're going to talk about here is all theorems today in 3.4. So the next theorem that we have in this case is called a rational zero theorem. Okay. What is this? All these are important. So make sure. What is a rational zero theorem? The word rational means fraction. Okay, so this will actually give us a fraction, p over q, where p in this case is the factor of your constant term, and q in this case is the factor of your leading coefficient. And we have put plus minus in here. So when you have what is a rational zero theorem? A rational zero theorem is actually telling us a possible rational zero. So what happens to this important theorem says that if I give you a polynomial function and I did not give you any zeros, because no zeros is given to you. So my question to you is, how do you gonna find the zeros here? Are you gonna perform syntactic division a lot of time till you end up with a 0? Because this time you're gonna try 1. Oh, you do the the 1, the 3, the 6, the -5, and the 9. So if you do the syntactic division here, you find out that you have to do it like a lot of time. The reason why is because you doesn't know which one is a 0 until you proven that this is 0. This is what you did in syntactic division in 2.3. So I didn't provide you any zeros at all. And if 1 doesn't work, you have to try -1. So it's like a jigsaw puzzle or Sudoku that you guys playing, that you have to play. It's like a try and error. So you have to play with all these numbers. So you have to end up with a 0 in here. Do you know how many times you're gonna try it? If 1 and -1 doesn't work, you have to try 2. 2 doesn't work, -2. Don't forget, it can be fraction, it can be square root, it can be imaginary. So what you're doing here is you keep on trying this forever, until at one time when you try one number, you end up with a 0. Do you know that that is so tedious? And in your test, you don't have time because you got only an hour and a half to do it. So what do we do here is you can list out all the possible rational 0 here using this rational 0 theorem to figure out. So some of these numbers you do not even need to try. For example, how do we use this rational zero theorem based on this polynomial? So the constant term here is 9 and the leading coefficient is 1. So in this case, you have to give me all the factor for 9. So can you guys tell me what times what is 9? Anyone?
3 times
Besides 3?
besides 3, 9 times 1.
So that is all the factors, right? For 3. For 9. 1, 3, and 9. Because 1 times 9 is 9, 3 times 3 is 9. That's it. We don't have, that's all the factors. And the good news about this is the factor for 1 is just 1. So what we do here is this is your P and this is your Q. So you will divide. So P in this case is 1, 3, and 9, all the factors for the constant term. And Q in this case is 1. So in this case, if you take, and then you have to divide. So you take 1 divided by 1 is 1, 3 divided by 1 is 3, and then 9 divided by 1 is 9. And don't forget, when you do the rational zero theorem, you will have the plus minus. So what's the plus minus means that instead of just 1, 3, and 9, it can be also negative 1, negative 3, and negative 9. So these are what we call as the possible rational zeros. So when you guys do your online homework, when they ask you to list all the possible rational zero, this is what you do. So in this case, you just need to divide with just these numbers. So instead of doing, so we're not going to try 2. The reason why we're not going to try 2 is because 2 is not on this list. We're not going to try 1/3 because 1/3 is not going to be on this list. So in this case, we can try like 1 example. This is just example. So, and 1 does not work, you try 3. 3 does not work, you try 9. 9 does not work, you try negative 1. Eventually, one of these will work. You will, when I say work, it means that your remainder is 0. So this is what we call as the possible rational zero in this case. Okay, so this is how you list it. So you look at your constant term, which is your P, and your leading coefficient, your Q. So this is called a rational zero theorem. Okay, very important. All these things we are talking about here is very important. 3, the conjugate theorem. Now, what is the conjugate theorem in this case? That conjugate theorem telling us that if you talk about 0 in complex number, it comes in pair. So when you have a complex number, it comes with pairs. And the pair in this case has to be conjugate. So in this case, that A plus BI is 0. A minus BI automatically will be 0. So that's why when you have a complex or imaginary part, it always comes in a pair. And the pair is always A plus and A minus BI. So for example, that if you find out that 3 plus 4i is a 0, then 3 minus 4i automatically is a 0. So they always come with a pair. So when you talk about this, you cannot have one imaginary. You always have to have 2 or 4 or 6 or 8 because it always comes in a pair based on this theorem. Okay, this theorem also works for square root. So conjugate of the square also is working. For example, is 3 plus root 5 is a 0. 3 minus root 5 is also a 0. So this is conjugate theorem, works on two types of pairs, two types. One is the complex and one is the square root. So if you got yourself a 3 plus root 5, automatically 3 minus root 5. If you got a root 7, then automatically negative root 7 is also 0. Same thing over here. So if you find out that 6i is a 0, automatically negative 6i is also 0. You guys clear with this zero, the conjugate theorem? So these are very, very important theorem in 3.4. You guys with me? Any questions you guys have with this 3 theorem? There are more, but this is the basic 3 theorem.